4A. All right. We answered the questions about calculus using calculus, which kind of makes a little bit of sense. Huh? What? Why? Oh, I put a blue background. Did you just notice? Yeah, school pride. I could have put red, but anyway, let's think about what the graph of 3 plus sine of x looks like. Also known as sine of x plus 3, right? Yeah, that's our Sahala graph shifted up 3 units. So if I draw that graph, let's see. There's the y-axis, there's the x-axis. Sahala would be, let's see, I kind of work, there we go, something like that. And that would be 2 pi. And if I move it up 3, let's see, that would be moving it up 1, right? Where it bounces on the x-axis. And then moving it up 3 might be up there-ish. And then here's my new y-axis. I know that 2 pi is still going to be right here. And then this is the halfway point. This would be pi. The sinusoidal axis could be the page divider, looks like. And that would be 3. And it would go up 1 unit to 4 and down to 2. So there's what the graph looks like. Now answering this question, if we knew we could sketch that quickly, and we're looking at the graph from 0 to 2 pi, notice the graph is concave down like a frown from 0 to pi, yeah? And concave up like a cup from pi to 2 pi. We could have answered the calculus questions without having to do calculus. Who knew? Well, we did. We did. So if this were like a multiple choice question or something, and you didn't have to show any work, that's how you can answer the question. Probably wouldn't be given something this simple on a free response question because it can be answered without using calculus. Is that legal, though? Totally. Yeah, we're going to be using calculus to kind of give us information about a graph, but you can also use your knowledge of what a graph looks like to inform you of what the calculus is doing. So feel free to use any and all mathematics, maybe even any history or English, or what other subject is there? BAN. If you find BAN helps you in doing a problem, feel free to use it. What else? What other subjects are there? There's a science there, discipline, yeah. So, What's that? Interpretive dance. If you find home economics helps you. Yoga. Nutrition. All right, letter B. Whoa. Take stock of what you have before you just jump in and start BOTCing. Simplify when? Early and often. Okay, so I'm going to distribute this and get this. Right? Yeah, that's right. Yeah, no, that was good. That doesn't work. That's not what I would do. In fact, maybe to understand what I'm facing here, I might just rewrite it like this, yeah? Okay, cool. So let's see what we can gather without having to do any calculus, just some of the information that we already have at our disposal. How about some of the easiest, like a y-intercept? That's real easy. What's the y-intercept? 2. So it's going to be right here at 2. What else do we know? Let's see. How about the end behavior? What's the limit as x goes to infinity or negative infinity? 0, right? So there's a horizontal asymptote on the x-axis. It's positive everywhere. I can tell that. 6 is positive. X squared plus 3 is positive. So I know it's going to live entirely above the horizontal asymptote. Any symmetry going on? If you replace x with negative x, you get the same output. So that function is even and has y-axis symmetry. So I'm guessing the graph has to look something like this. I'm guessing. And something like that by symmetry. So it'll take on what resembles possibly like a standard normal curve in statistics. Sorry to bring that up. Right, in statistics. Huh? Yeah. So just looking at the graph, I can answer some calculus questions, right? Like I know that the graph of this function is increasing for all x less than 0. Yeah? Hi, Iris. Iris. I can combine the two. I'll do that from now on. Iris. Hi. Instead of hi, Iris. I can save time by just saying Iris instead of hi, Iris. I can also tell that it's decreasing to the right of 0. I can tell there's a local maximum at 0. I can get all that calculus information just from the graph, right? Well, we're looking at curvature information. Is this graph concave up or concave down? Yes. Whatever you said, it's correct. It is both. It is both. In fact, as you come in from the left, it's part of a really, like Mona Lisa smile, right? Like, kind of real gradual and subtle. Up to about right there, right? And then it goes to concave, down like frown. That'd be like a horrible Native American name, right? If you were known as concave, down like frown. And then it's concave, up like cup, right? That's the guy everyone want to be around, concave, up like cup. So just looking at this graph, if I knew one of those x values, I think I'd have the other one, right? Because of the symmetry. I'm no fool. I walk up there and I'm just like, yeah, that's going to be at, not as obvious, is it? Now, if this were the standard normal curve, if it happened to be the standard normal curve, and that was mu, I would know that this would occur at x equals mu minus sigma, and this would occur at x equals mu plus sigma. I would know that, right? Because maybe you've learned in statistics that that 68% roughly of the population, or the things that occur, happen within one standard deviation of the population mean. And guess where the first standard deviation falls? Always at the inflection point is where the first standard deviation is. But that doesn't help me in this case, right? But there is statistics-based, calculus-based statistics, and probably statistics-based calculus, right? And probably, I'm sure, calculus and statistics-based interpretive dance. I would love to see that. And so knowing the location of these critical value, or these inflection values, is pretty important for statisticians. We're going to have to BOTC now to find them, aren't we? We don't want to guess because we could be wrong. We want to have better odds than that. So I guess it's time to take the derivative. You want to use the first version or the second version to take the derivative? Me too. One of them. I'll probably choose the first one, just because it's lightning quick chain rule. The other one's a Hody high. So here we go. F prime is going to be -6 times x squared plus 3 to the -2nd times the chain rule, 2x. And simplifying before I proceed, cleaning that up a little bit, tidying up, I get f prime equals, that's going to be a -12x times an x squared plus 3 to the -2nd. From here, you have the option of product rule again, or clean it up and do the Hody high rule, because it does have two factors. What do you want to do, product or Hody high? It's already set up for product, right? Yeah, let's go ahead and do product. Might as well. I'm going to call -12x the first factor. F double prime. Here we go. We got -12 times x squared plus 3 to the -2nd. Minus 12x goes along for the ride, times the derivative of the second factor is -2, x squared plus 3 to the -3rd, times another 2x. Now remember what we're after, what we were after with the first derivative is really the same thing we're after now. We're after a full-fledged factored version of the second derivative that is a single term, so that we can use the numerator and denominator very quickly. So what I'm going to do is clean up the second term, because there's a lot going on there. I don't want to mess anything up. I'm going to have a negative times a negative, so that's a positive. I'm going to have a 48, it looks like, x squared times an x squared plus 3 to the -3rd. Now, the coolest, funnest, most efficient, awesome way to get to a single factored version of your derivative, if you have any negative exponents at all, is to factor out least powers. And that's an awesome algebraic trick. It's almost like magic. If you go to college and you're doing this in front of your peers, they're going to just be marveled at your wizardry. Okay, and they're going to demand to know the secret. All right, so let's go ahead and do that. We'll factor out least powers. So we can factor out a 12 or a -12. What would you prefer? I have a tendency to pull out the negative as well. Okay, no big deal. There's no x, unfortunately, but there are some x squared plus 3s. And which one do we pull out, the -2 or the -3? The -3. So the lesser of two powers here. And then we go to the beefy pink bracket, which is not as brown as the brown one, but just as strong. Of course, we have a 1 left on the negative 12, but we are left with some residual x squared plus 3. And remember, to get the new exponent, we do what we started with, exponent, minus what we factored out. So negative 2 minus negative 3 is really negative 2 plus 3, 1. So we don't even need parentheses around there. Sweet. And then I have a negative 4x squared. That's what I get in the second term. That's awesome. And then here we go right to the final answer. I'm going to have a negative 12 on the top. Everything in the beefy pink brackets now I can combine. And it's over x squared plus 3 cubed. And then the numerator, I'm going to have a 3 minus 3x squared. Now, you could stop there, but what I would do is factor out a negative now from the inside and a 3. So that's going to make a positive 36 out front and a positive x squared and a minus 1. What you're trying to do is kind of avoid so many negatives so that when you plug in, things work out. So if you factor a negative out from 3 minus 3x squared, a negative 3, that gives you a positive 36 up front. And, of course, the 3 is gone, and I commuted the terms. Now, you could go one step further, right? X squared minus 1 is the difference of squares. But the whole purpose of getting to this step is so that you can look at it at a glance and determine the roots of the top and bottom, which I think we can figure out from x squared minus 1. And so that when you plug it back in, you can figure out what the signs are. So I think x squared minus 1 is small enough that I can manage that. All right, so here we go. F double prime equals 0 when the numerator is 0, which is when x equals what? Plus or minus 1. So that's about all the work you would need to show. F double prime equals 0, got it, know what you're doing. Looking at it, okay, sweet. Does F double prime ever equal DNE? Does the denominator ever equal 0? No. Okay, so there's none of those. So we only have 2 PIVs, possible inflection values. Now, of course, since we know what the graph kind of looks like, we've got our answer, don't we? For intervals of concavity and everything. We know that this is negative 1, we know this is positive 1. But let's say we didn't know what the graph looked like. What could we do? We can make a little number line chart. X, F double prime, negative 1, positive 1. There's no discontinuity, so we pick some values like negative 2, 0, and 2, and we plug them back in right here. Now, as you're plugging into your derivatives, whether it's the first derivative or second derivative for the sign only, just kind of look at it and say what actually matters. 36 isn't going to change the sign, is it? So I'm not going to plug into 36. There's nothing to plug into. But I'm not going to multiply my answer by 36. It takes a while. And the bottom, even though it's cubed on the outside, cubes kind of preserve the sign of whatever's on the inside. The inside is always what it is? Positive. So really the whole sign of the second derivative is determined exclusively by x squared minus 1. Which, if you just want to imagine a parabola open up, you know it goes from positive to negative to positive. You got it. Or you could just finish the chart out since you started it. Negative 2 squared is 4 minus 1 is positive. Who cares? Plug in a 0, you get a negative. Plug in a 2, and you get positive 3. So again, you get no credit for the chart, but it does help you organize your information. So as we kind of were expecting, using a chart or the graph, F is CC up on the interval from negative infinity to negative 1, union 1 to infinity. F is CC down like a frown between negative 1 and 1. Oops. And if we had to justify the inflection points, I think I'll just say the sentence because it's a lot of writing and I'm running out of room. But you've got it down, I'm sure, from the first derivative. F has an inflection value, not a PIV anymore, but an actual inflection value at x equals negative 1, since F double prime changes from positive to negative at x equals negative 1. Can you clump those two together? Could you just say that F has inflection values at x equals plus or minus negative 1, plus or minus 1, since F double prime changes signs at each of them? No, and they change differently, don't they? So you'd have to say a separate sentence. Additionally, comma, F has another inflection value at x equals positive 1, since F double prime changes from negative to positive at x equals 1. you have to always say how the sign changes. Okay. Any questions on that? That time we got pretty far without having to be OTC. But there were certain calculus questions, namely the inflection values, that we couldn't just eyeball and pick up from the graph. All right, this one here. Should I let you kind of start it on your own for about 5 minutes? I'll let you do it for about 5 minutes. Okay? And see how far you can get into the second derivative. And then we'll come back and look at it together. This will be the part of the video you might want to fast forward. Or try it on your own, heaven forbid. Yogi Berra said you could observe a lot by watching. He was right. You can learn a lot by doing. While y'all are doing that, if you were not in here during lunch, we have postponed this Friday's examination to December 1st. That's the Tuesday we get back from Thanksgiving. Now it's on an odd day, not an even day like we're supposed to. But if there's no objections, we'll stick with it. So no test this Friday. Yes. I won't be here that day anyway, so it kind of works out nicely. A substitute can just hand out the test to y'all. It looks like many of you are doing the Hody High rule, which is exactly what I would do. Then you kind of clean up the numerator. You shed a few pounds doing that, burn a few calories. And then you get to the second derivative, and you're just like, really? I got to do all that again? Sometimes getting to the second derivative is labor intensive. I'll see if I can kind of catch up with some of y'all without making a careless mistake. Y'all keep going. That's anticlimactic. Let's talk about efficiency in doing this. When you do the Hody-High rule, you're going to end up with, of course, a single fraction, but you'll end up with two terms in the top. So it's like the product rule with the denominator, but that kind of unifies it. Before you, when you're simplifying, before you start expanding things out and then combining like terms and then trying to factor it, remember that when you take the derivative, it's already partially factored. Each term is partially factored. So if you can get in the habit of first looking for a common factor in each of your two terms, it's going to simplify everything after that. So I noticed that there's a 2x common up there. So if you factor it out, you're left with x squared minus 4, and then distributing the other negative, you get minus x squared minus 1. That cleans up real nicely to get negative 10x over x squared minus 4 squared. So, of course, we have a critical value, don't we? Where's our critical value? What value makes that 0? 0. And what values make it undefined? Plus or minus 2. But are those critical values? No, because they're not in the domain of the function. In fact, I know that those at x equals plus or minus 2, we have what? Holes or VAs? They're VAs. So I know they're going to make it into the chart, but they're not going to be critical values. You can actually quickly determine if that's going to be a local max or a local min, because notice the denominator just to the left of 0 and to the right of 0, well, it's going to be squared, so it's positive. So if you plug in just a number to the left of 0, you're going to get a positive number. If you plug a number just to the right of 0, you're going to get a negative number. So G prime changes from positive to negative at x equals 0. So it must have a what there? Local maximum at x equals 0. We didn't do the number line chart. But we're after the second derivative, right? After this first derivative stuff. We're going to keep going. Hody-High minus Heidi-Ho over ho-ho. Oof. That's pretty complicated. So once you get down to here, again, take notice of what you have. You have an x squared minus 4 and an x squared minus 4 that's common. If you factor it out with the beefy green brackets, it's a nice bracket set, you're left with negative 10 times one of the x squared minus 4s. Negative times negative is positive. You end with a 40x squared over that to the fourth. And then, of course, you get a negative 10x squared plus 40x squared. That's 30x squared plus 40. Factor out the 10. It's a quick way to get down to here. Now, we did all that hard work. Get down here. G double prime is equal to 0 when the numerator is 0. Well, that's when 3x squared plus 4 is equal to 0. What real numbers make that happen? None. Gosh dang it. So there are no values that make G double prime 0. So there's no PIVs. When is the denominator 0, though? Because that's when G double prime is undefined. Well, that's plus or minus 2. Are those PIVs? No, we already said they're what? VAs. So they're in the chart. You know what? So all that hard work to get down to here just to see that there are no PIVs. Well, if there's no PIVs, are there any IVs? No, you got to have the PIVs before you can have the IVs, right? You got to have the PIVs before you can remove the P. So there's no inflection values. Bless you. Bless you. Now, just because there's no inflection values, does that mean that the graph is either concave up or concave down over its entire domain? No, because where else can a graph change its curvature? At discontinuities, yes. So, at asymptotes. So let's go ahead and try it out here real quickly. We got x, then G double prime. And we got negative 2 and positive 2. Those are your two vertical asymptotes. In fact, I'm going to draw them like this because I don't want to get them confused with actual values. How about a negative 3, 0, and a 3? Plug in a negative 3 and you get, top is always positive, right? X squared minus 4, when you cube it, the cubit preserves the sign. So notice the sign of all of G double prime is determined by x squared minus 4. Would you agree? And x squared minus 4 is a parabola that goes from positive to negative to positive. So really, that's all you have to do, or just plug them in. So this graph you can now say is concave up for all x less than negative 2 and all x greater than 2, and concave down between negative 2 and 2. Now, having done all that, that was a lot of fun calculus. Maybe we could have been like, you know what? I kind of recognize that graph. I know the domain is the set of all x such that x can't be plus or minus 2. In fact, I know they're vertical asymptotes. Let me just shrink all this down, space bag it, right? Suck out all the air, put it under the bed. There we go. What if you had like 5 space bags full of like shrunk down sweaters? And then you put all of those in a space bag. Would the sweaters disappear? All right, negative 2, positive 2. Those are vertical asymptotes. Yeah? You always graph asymptotes first. How about the end behavior? What's the limit as x goes to infinity? Being at 1x squared over a 1x squared. It's 1, right? Leading coefficient over leading coefficient. What's the y-intercept? Negative 1/4. Even, odd, or neither? Even over even is even, so it has y-axis symmetry. Any x-intercepts? Is x squared plus 1 ever 0? Not in the real world. So I know what the graph looks like. To the right of 2, it has to look like this. Otherwise, it would have x-intercepts, right? By symmetry or the same argument, it has to live above the horizontal asymptote to the left of negative 2. It has y-axis symmetry and no other x-intercepts, so it has to turn down. I could generate that graph right there without having to BOTC at all. Did I answer all my questions? This function, of course, is increasing for x from negative infinity up to negative 2, union negative 2 to 0, decreasing from 0 to 2, union 2 to infinity. There is a local maximum, as I anticipated, at x equals 0. Let's talk about concavity. This graph is concave up like a cup from negative infinity up to negative 2, union 2 to infinity. And it's concave down from negative 2 to 2. Where did the curvature change? The only place it changed was at the vertical asymptotes, which means I know there's no inflection values. I could have answered the questions like that without doing all that wonderful, awesome, delicious, good for me algebra. We got the space bag it, right. Was this algebra in hindsight for nothing? No, right? It's all good practice, right? But it's also good practice to kind of have a strategy, depending on what type of question it is. Of course, if this were a free response, I would probably require you to show all the work. But a question like this that could be answered exclusively from a graph, you can get calculus information from a graph that you generate, would be a nice multiple choice type of question, right? So think about a strategy before you just jump in and start doing stuff. Okay, awesome. We'll pick up with the last 3 on this example. We'll probably quiz tomorrow. And now the test is pushed till next Tuesday. Or not next Tuesday, my bad. We have a whole week off next week. Like forever Tuesdays from now. We can just keep going, right? Just keep going. Have a great day.